Hello, this presentation covers our conceptual design view that is over our senior design project in which we had to design a nano brewing system. This presentation is prepared by myself, Samuel Ball, as well as my classmates listed below, and it is prepared for Dr. Tipton and Dr. Moran. And so our clients presented the idea of a small-scale brewing system to be used in the Intro to Brewing Science class that is offered during the spring. In the chemistry department, the University of Tulsa has been offering this class for the past couple of years, and now with increasing enrollment, they need an improved and upgraded brewing system from what they currently use. Our statement of work consists of the purpose, scope, location, deliverables, acceptance criteria, schedule, and standards, which can be viewed in more detail from our written prototype report. Moving on to the team responsibilities. In order to achieve our project's overall goals, we start off with brainstorming, in that we came up with possible concepts that could be implemented further. And then from there, we went into researching and we went to local breweries to gain feedback and perfect our design. And we'll talk about the development and testing in another slide. So for the brainstorming, we looked at various components that are involved in a brewing system and implemented those components into concepts based on the constraints we were given. These include the hardware for the nano brewing system, such as the tanks and modularity, the electrical system, such as the heating elements and the pumps, and the accessories, in which we looked at concepts for the mixing element. And lastly, we determined the size and shape of the frame based on where it was located in the lab, as well as the materials that could be used that would be FDA approved. And then again for the research, we went ahead and visited breweries, we researched appropriate materials, and we also read forums and consulted industry experts, as well as consulted Dr. Sheaf and Professor Simcox for any concepts that had any issues to the constraints that we were given. So for the development and testing, we plan on getting components such as the heating elements and pumps configured into our system, as well as manufacturing the frame and the mixing element next semester. And so the next slide will talk about the customer and the requirements.
So I'm going to talk about customers and requirements. Our customers are Professor Simcox and Dr. Sheaf from the chemistry department at TU. These professors offer a class during the spring called Intro to Brewing Science. This class focuses heavily on the mechanics of brewing, the basic chemistry of fermentation, and water chemistry. It also explores the history and styles of brews. At the end of the course, the students take an exam given by the Institute of Brewing and Distilling to qualify for the General Certificate in Brewing. The IBD is an international acclaimed brewing and distilling institute located in London, England. Students that obtain this qualification obtain one of the most widely recognized brewing qualifications in the world. So what the customer wants us to do is to scale down a standard brewery size. Now, there are many commercial smaller scales systems available, but not quite as small as this professors want. They have very specific constraints and requirements since they're in a laboratory environment and not factory environment. Some of the requirements that the professors gave us is that it must be electrically heated, no larger than 110 volts, so the standard outlet that you find in any household. It must have a vertical layout since it's going to be in a countertop for the lab. It must have a grain mill in order for the students to be able to manipulate the grains that go into making a beer. It must be desktop size as mentioned before, because students must be able to do it in the lab countertop. It must be easy to maintain and modular. The focus of the students is beer brewing, not the hardware itself. It cannot be bigger than 3.5 gallons, since that's too much and they would be wasting water and grains. And it must have a control system for the students to be able to manipulate all the systems that go into brewing beer.
So I will be talking to you about a few of the concepts that we came up with before reaching what we think is our final design and what we want to move forward with. And Jacob will talk more about that design. I will only talk about what we ended up scratching, or maybe what inspired our final design. So after a first meeting with our customers, we decided we wanted to try a 2-tank system, such as this one, with connectors between the tanks. So this would be the bottom tank and this would be the top tank. And we would have a connector between these 2 tanks so that they'd be rigidly attached whenever we want them to be stacked on top of each other. And also design connections for the accessories related to the brewing process. So in this case, the grinder could be fastened to the top, and we would put grain through the top and crank this handle, grain would fall, and then we would be able to remove that. And after that, we'd be boiling water down here, and we'll pump that up and have this stirring element mix the mash in this upper tank. But we figured out that this would be a huge hassle to have to clean after every batch. So we scratched that idea, and we decided to expand on this connector and create this mash removable accessory, a stir that would have rotating paddles. And we thought about adding a secondary heating source to this device so that we could ensure a proper temperature distribution, or a consistent temperature in the mash. But we brought this idea to our customers, and they said that they didn't think it was a good idea because being in direct contact with a hot element could burn the mash or cause inconsistencies in the sugar release. So we decided to strip that idea and create a stir that only had the paddles. But the problem with that is that now we need a heating element somewhere else, and we did not want to invade or be too invasive with the tank. So we figured, why not do like a stovetop type heating, or like a heating table or a heating plate. So we moved to this idea, which is a lot more convenient. We build a frame for the with multiple levels for the major heating element and the minor heating element to sit, and then have the tanks sit on top of those and build the everything else around that. And this is what we've been pushing into our final design. And also after the wort, the purpose of this is to prepare the wort, and then the wort has to be fermented with the yeast and the hops and all those other ingredients. And so it has to be moved to a different container for that to happen. And we have been designing that to look something like this. It'd be a cylindrical container with conical ends, and it would open up at the top and converge at the bottom. And the reason for this is that we want the sediment here, all the yeast, to collect, and we want to be able to extract that with a valve and reuse that, because that can be reused for further batches and make the whole process cheaper. And also this cone, this opening at the top, is the idea is to, during fermentation, there's a lot of foam being produced and excess gases. So we want that foam to have as much space to be in, so that there's no overflow. And we still have yet to design a lid that would allow one-way flow for the excess gases to go out, but nothing to go in, especially bacteria. And obviously, for this fermentation tank to sit upright, we would need to create a stand such as this one to kind of hold it in place, because otherwise it would fall over and make a huge mess.
All right, so now we're going to be looking at the final concept as it is planned right now. And so we're first going to be looking at the SolidWorks model, which was created to test the sizing and feasibility of the design as a whole. And then next we'll be looking at an animated demonstration very briefly to show the equipment that we are responsible for as stated within the scope. And this will also hopefully bring some insight into the brewing process, into the goals we are trying to achieve. And then we'll be looking at our prototype, which was created to test the structural feasibility of our design. So first, looking at our SolidWorks model, we have a couple of views here from isometric views, and it's important to note that the model does not include some of the external deliverables that are within our scope. And so this includes the grinder, the immersion chiller, stirrer, fermenting tank. And the reason these weren't included is because they're more of standalone pieces as opposed to the towered tanks. And so they don't require the same level of engineering in their implementation. And so as you'll see in this model, the frame is entirely designed from aluminum extrusion, since it's readily available, affordable, sturdy, and just very customizable. And the pumps, valves, and hot plates are all depicted with their relative sizing to show their proposed placement with respect to the other components within the model. And so looking at a cross-sectional view of the model, we kind of see the straining aspect of the top tank. And so that false bottom plays a really important role in preventing large grains and particles from passing through onto the next step. And so once sugar has collected there, then hot water is used to sparge out the remaining grain sugars onto the next step. And so to get a better view of this and all of the processes that we're looking at within the brewing process, we're going to be quickly going through the animation. And so in the first step, we're going to apply high levels of heat to bring the water in the bottom tank to a boil. And then that water is pumped up to this top tank as shown here. The grains are now grinded externally, and then these grinds will be added to the hot water as shown by this color change. And then the top tank will be heated with a lower level of heat than was used for boiling while it is being mixed to incorporate sugar. And then a valve will be opened up to drain that new mixture into the bottom tank again. And then this hot water is boiled and then is used to wash out the remaining sugar that was left on top of the false bottom. We then remove the tanks and pipes, and then we're going to stir in the hops while it's being reheated. And then in this step, an immersion chiller is inserted, and then it's either pumped through or using a faucet to run cool water through the immersion chiller and then out the other end. And this is continued until the desired temperature is reached. And then the liquid will be drained into a fermenting tank. And then here is where yeast is stirred in. And so this step shows the yeast being stirred in gently. And then an airlock is put on top to prevent air from entering but allowing gas to escape. And then after this step is complete, the uncarbonated beer can be collected, and then the leftover material can be reused in future brews if desired. And those are your two products of the entire process. And so now with this understanding of the process and the digital models created, the initial prototype can be discussed. And so the prototype uses stainless steel pots as tanks. And this is done because their surfaces are food safe and they resist scratches more so than other materials like plastic. And those can be really detrimental to the ability for the tank to stay clean. And so if there's any scratches, then sugars can build up and that can cause mold over time. And so the prototype also uses a PVC frame, which is used to test the fit of the pots into the frame and their ease of maneuvering into and out of the entire contraption. And on the right picture, you can see that the top tank has a stirrer and a false bottom attached. And so while it doesn't necessarily ready yet for components like the motor, the pump, and the temperature control, all the electronic components, the prototype did provide crucial insight into the buildability of the final model.
In this section, we'll be talking about the quantitative engineering specifications for our project. So the specifications and design criteria for our project, we first started by going to our customer and finding out what their needs were. And then from those needs, we created specific engineering specifications for the project. We also adhered to the engineering regulations and safety considerations that are put forth by OSHA and the Electronic Code of Federal Regulations regarding beer brewing. When the University of Tulsa Chemistry Department came to us, they asked that we design a low-capacity beer brewing system so that each student in their brewing classes would be able to individually brew their own batches of beer. Usually commercial systems only go down to 5-gallon tanks, but we decided to design a system that would end up brewing 2 to 3.5 gallons of beer. They also asked that the system have a minimal horizontal footprint so that each one could fit on the top of a student's lab table. Our final design will fit within a 3 by 3 foot area. The system also needed to be lightweight so that the students can move it from storage to their lab tables readily easy. We decided to use a modular design where each component of the design will weigh less than 25 pounds so students can easily move them around. Using our final design, the University of Tulsa plans to recreate more for their brewing classes, along with a commercial option for local universities that also have brewing classes. They asked that we keep the entire system cost under $1,000 so it's economically viable to recreate. They also asked that there would be a high power heating element in the lower level of the system. This main heating unit will need to have the capability of heating 3 gallons of water from room temperature to boiling in less than 30 minutes so that the professors can have the lab completely ready to go by the time students arrive. Along with the high power heating element on the lower level of the system, they asked that we have a low power heating element on the upper level of the system. This auxiliary heating unit will need to be able to keep the mash temperature at 150 degrees during the entire mash process. When brewing beer, it's important to rapidly cool the beer before fermentation as to not kill the yeast. We've decided to use a counterflow heat exchanger while the beer is being pumped from the brewing system into the fermentation tanks. This system will also need high electrical efficiency as the entire brewing system will need to be powered by 110 volt wall outlets, which is the only electricity source in the lab rooms. They also asked that we design a control system to control the temperature and the pumps. When brewing beer, it is vital that the temperature stays relatively the same throughout the entire process depending on the beer you're brewing. We will design a control system to keep all tank temperatures within 5 degrees Fahrenheit of the input temperature. This system will also be able to act as an on and off switch for the pumps throughout the brewing process. Safety was also a high priority for our customers. They asked that we have safe heating elements for the entire system. Usually commercial systems run off open flames powered by propane. Instead, they asked that we use electrical heating units instead of the open flame design. Safe operation is also vital for the project. Students will be using this, so we decided to put the boiling water tank on the lower level of the modular system in order to protect from spillage. Along with all the customers' wants, the brewing system will also adhere to the following codes and standards. We've employed the OSHA standards pertaining to electrical safety, laboratory chemical safety, temporary heating devices, pumps and pumping equipment, heat exchanger safety, and storage tanks. Along with OSHA standards, it will comply with the Electronic Code and Federal Regulation standards pertaining to necessary beer brewing materials, construction of brewing systems, and testing of brewing systems.
All right, so now we're going to talk about potential safety issues and hazards that we've identified pertaining to our system, and then also some potential regulations and codes that we might have to look into and follow. So we came up with 3 potential hazards that our system's going to have. We're going to have thermal, chemical, and electrical hazards. Our thermal hazards are going to come from exposed surfaces that are hot, like our hot plates, or when our tanks are getting heated up. The solution to this really is in the system itself, is that we're going to have a frame around it. So for anyone to burn themselves or anything like that, they're going to have to intentionally reach past the frame and touch any of these hot parts. So hopefully that is enough to keep accidental burns from happening. Electrically, we'll be moving liquids around and we'll be using electrical equipment, so we have electrical hazards. Solution is this: keeping wires covered, keeping things turned off when we're not using them, keeping the equipment from leaking, so keeping it updated and safe. And then chemically, just when we're cleaning, we're going to use chemicals. So really, for all these hazards, we need to make sure we're using the right equipment, make sure we're using it correctly, and then for anything we want it labeled. We want the chemicals labeled. We're going to want anything hot labeled, and any electrical hazards, potential electrical hazards, we're going to want those labeled too. The one code kind of regulation that we might fall into is the boiler and pressure vessel code, since we're going to be heating up a liquid in this contained vessel. We're going to create some pressure, so we might have to look into that. Initially, we kind of think that the system's small enough that it's not going to fall into the boiler and pressure vessel code, but it's still something that we could come back to and look at and check just in case. So from safety, we're going to move on to our budget. So just a brief summary, our max budget is $1,000. From what we see, almost all of it, or a large majority, is going to go towards materials and parts. And then our self goal is that we're going to be able to have this compete on the market with systems that are already out there. So this is our actual budget breakdown, and without getting into it too specifically, on the left we have our customer costs, and on the right we have our total project cost. The customer costs are going to be the cost, what the customers are actually going to pay for, and as you can see, it's just mainly going to be materials and parts. At the moment, we only have a few things in. We have our stainless steel pots, which are going to serve as our tanks, but a lot of the other stuff we're having to estimate. Based on our estimations, though, we're well under budget. We still have half the budget for any expense that might pop up, anything that turns out to be more expensive than we've estimated. We have plenty of additional funds that we could rely upon. The total project cost, however, is well above the budget we agreed on, mainly just because any engineering time and machining time just added so much cost. And as of right now, we've spent most of our time working on software. We're estimating that we're going to put a lot more time into our hardware design, testing and analyzing that, and then probably going back to our software to redesign and then finishing with the hardware. And in there we're going to have some time to machine, so we're also going to add an estimated machine time, which is going to just increase our cost. So lastly, we just have any questions you might have. So thanks.